You know that on the basis of the type of force that holds the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with metallic solids. In metallic solids, the metal atoms, such as copper, iron, silver, and magnesium, lose their valence electrons to the crystal as a whole. These solids are merely a collection of positive ions surrounded by and held together by a sea of electrons. Hence, the constituent particles in a metallic solid are positive ions in a sea of delocalized electrons. The electrostatic forces of attraction between the positive ions and the electron cloud constitute the metallic bonding, which holds the positive ions together. These electrons are not localized on any atom, but rather delocalized uniformly over the entire crystal. These free and mobile electrons make metallic solids good conductors of electricity and heat. The electrons flow through a network of positive ions when an electric field is applied. Similarly, when heat is supplied to one corner of a metallic solid, the free electrons spread the thermal energy evenly throughout the solid. The presence of free electrons also accounts for the luster and color in some cases. Metals are highly malleable and ductile. Metallic solids have fairly high melting and boiling points. The other type of crystalline solids is covalent or network solids. The constituent particles in these solids are atoms. These atoms are held together in large networks by covalent bonds. This interlocking network of covalent bonds extends throughout the crystal in all directions. Hence, covalent solids are also called network solids. They are also termed as giant molecules. Diamond, graphite, and quartz are some network solids. As the atoms are held by strong covalent bonds, these solids are very hard and possess very high melting points. These solids are non-conductors of electricity, except for graphite. In diamond, each carbon atom is bonded tetrahedrally to 4 other carbon atoms. Thus, a regular tetrahedral arrangement of carbon atoms bonded to one another in a 3-dimensional manner forms a network, resulting in a rigid giant molecule. Note that diamond is the hardest substance known and has a melting point of 3,550 degrees Celsius. On the other hand, graphite is an exceptionally good conductor of electricity and is extremely soft. In graphite, each carbon atom is bonded to 3 other carbon atoms, resulting in hexagonal rings, which, when repeated throughout a plane, form sheaths or layers. In its layered structure, the layers of hexagonal rings are arranged parallel to each other, as shown here. These layers are held together by weak van der Waals forces of attraction. The layers can slide over one another when impurities are present between them. On account of this, graphite is soft and can be used as a solid lubricant. As each carbon atom in graphite is bonded to only 3 other neighboring carbon atoms, the 4th valence electron is free to move about in different layers. Thus, the free mobile electrons account for the exceptional electrical conductivity in graphite.